Okay, so today we actually begin with an algorithm which is called Simon's algorithm. That was the first algorithm to show a clear-cut exponential speed up over a classical algorithm, even on a probabilistic classical computer. So we have seen before that Diaz-Souza algorithm did solve a problem that can be solved with an exponential speed up on a quantum computer with respect to a classical computer if you're looking for an exact solution. But if we are looking for a probabilistic solution with a very high probability, then a classical computer can also quickly solve it with only very few iteration as compared to the exponential. So the exponential speed of Diaz-Souza actually quickly dissipates if we have access to a probabilistic classical computer. Then we saw an algorithm by Bernstein-Vazirani where we were trying to guess a secret bit string that a black box was using to multiply the input with and give the output at one of the output terminal which we used as a phase in a phase oracle. That algorithm actually does provide a polynomial speed up because we were able to solve that problem with a single query on a quantum computer, whereas on a classical computer, you need n queries, where small n queries, where small n is the number of qubits. So it was not an exponential speed up, but sort of a linear speed up. And then we saw another very important algorithm. It's called Grover search algorithm or quantum search algorithm, which we saw that can search through an unstructured database, and the number of iterations of an oracle are required that scale as the square root of the total number of entries in the database, which is a quadratic speed up with respect to a classical algorithm, because classically we might have to look through each entry in the unstructured database to find what we are looking for. So Grover algorithm gave us a quadratic speed up, still not exponential. And then I think before Grover in 1996, Simon came up with a problem that he solved, and he showed that we can have some problems which can be solved with an exponential speed up with respect to a classical computer. And it doesn't matter if your classical computer have access to a random number generator or not. Even on a probabilistic computer, it took exponentially many steps to solve the problem, whereas on the quantum computer, you took only like polynomial number of steps, not one step as in Bernstein and Diaz-Souza algorithm, but polynomial number step. And actually that 1996 algorithm of Simon inspired Peter Shor to come up with a problem to factor discrete, to find the discrete log, which, and then quickly he was able to come up with an algorithm to factor a composite prime number, and with an exponential speed up over a classical computer. That led to a huge interest into quantum computing, because for the first time there were algorithms that showed that quantum computers can be used to solve many classical problems with an exponential speed up. And all those problems like factoring problem and discrete log problem, they're practical problems that had applications in the world, especially in the communication regime, because the current public encryption, public communication, it relies on a type of encryption scheme which relies on the impossibility or inefficiency of classical computer to factor large number or find discrete logs of numbers. And all of these problems actually come down to sort of finding a period. which is done by a Fourier transform. So this Simon's algorithm actually also inspired quantum Fourier transform and quantum that we will study in tomorrow's class. And the quantum Fourier transform was then used to find discrete log and periods and factors of numbers, and have many more applications in a diverse area right now. And this algorithm that we are going to study, the Simon's algorithm, actually set a race for all of these algorithms. And there's actually a story behind it as well. So Simon developed this algorithm for this problem that he thought could be solved exponentially faster on a quantum computer, and sent a paper to a conference. And the conference committee, which actually included Peter Shor, rejected the paper. But Shor understood that problem, and he later was giving a talk somewhere. I saw the talk on YouTube, and he said that perhaps he should have been more emphatic with the committee member to accept the paper and publish. But anyway, the paper was rejected. But the idea was seeded in Shor's mind that, okay, this is a way that perhaps can be used to find exponentially faster factors of numbers on a quantum computer. And I think within 1 year he was able to devise this algorithm to find factors of composite number. And Simon's paper then got published somewhere else. Okay, so let me share my screen. And you can see one note. Okay, here's one note. All right, so today we are going to study Simon's algorithm. And in this lecture, I will first explain what is Simon's problem, so that we understand what the problem is. We will quickly discuss classical solution, and then we will go on to find its quantum solution or quantum algorithm. And before I implement, I will discuss how to implement Oracle for Simon's algorithm. And this is also a problem where we will discuss a new type of Oracle actually. So let me just write. So it's going to be a new type of Oracle than we have been introduced before. So it's not a phase Oracle. And then, of course, we will study its implementation and Qiskit. Okay, so let's start with Simon's problem. So Simon problem in a nutshell is like this, that you have a black box. And it has an n-bit input. And let's say we give some input x, and it implements a function f of x, and give us an output. And in this case, now we are going to assume if the input is n-bit, the output is also n-bit. So it's not a function that we previously used in Diaz-Souza and Bernstein-Vasiliani algorithm. It's a different function because it maps a state which is an n-bit state to an output which is also n-bit state. So it maps an input string into an n-bit string. However, this function itself can be of two types. So this f of x is either a one-to-one function or it is a two-to-one function. A one-to-one function is a function which maps each input to a unique output. Okay. And a two-to-one function is a function which maps exactly two inputs to one output. And our problem is to find out whether f of x is one-to-one or if it is two-to-one. That is Simon's problem. Okay, but let me explain the problem a bit more. So in summary, we have to find out if f of x is one-to-one or two-to-one. And let me just explain it a bit more, because that will help us in devising and understanding the algorithm. So let's say, since we are talking about digital functions, and if we restrict ourselves to a 3-bit input output, then x can be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. So these are 8 possibilities. A one-to-one function will map each one of these to a different output. For example, if it is a linear function, it can map 0, 0, 0 to 0, and 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, 6 to 6, and 7 to 7. And if I plot it, it's going to be something like this. So f of x is going to be like this. So actually, it's better if I draw these discrete line. 0, 1, 2, 3, 4, 5, 6, 7, 8. And you see that each of the input is being mapped to a completely different output. So for example, 1 is mapped to 1, and this one doesn't show up anywhere else. Similarly, 2 is mapped to 2, and this 2 doesn't show up anywhere. So this is a one-to-one function, because 1 goes to only 1. But this is not the only type of one-to-one function possible. There can be another one-to-one function like this. So I can also have, for example, something like this. I may map 0, 0 to, let's say, 0, 1, 1. I can map 0, 0, 1 to 1, 0, 0. I can map this 0, 1, 0 to 1, 0, 1, and then the next one to 1, 1, 0, and the next one to 1, 1, 1, and the next one to 0, 0, and like this. So this is also a one-to-one function. Okay, but its plot is going to be, something like this. So 0 is being mapped to 3. So this is, 3. This 1 is being mapped to 4. 2 is being mapped to 5. 1, 2, 3 is mapped to 4 is mapped to this, and 3, 4, 5, 6, 7, and then 5 is mapped to 0, 6 is mapped to this, 1, and 7 is mapped to this. So this is also a one-to-one function, because each input is being mapped to one output. And now you can think of, a lot of different one-to-one function. And actually, there can be a huge number of them. We can just have to prepare all possible permutations that are possible, So maybe this is this, this is this, this is this, this can't be this. So this, maybe this. So there are various combinations that are possible for these one-to-one functions. So any question about one-to-one functions? So Abdul Ahmed, clear? You're from math, so I think it would be easiest for you.
Yes, sir, I understand.
Okay, perfect. So let's now go to 2-to-1 functions and see some of the examples. Okay, so one thing that I want to stress that when we are talking about 1-to-1 function, it doesn't matter what the value of f of x itself is. What we are interested in, that one input goes to only a unique output, and this output doesn't show up in front of any other input. It doesn't matter what the value at a particular input is, as long as this output doesn't show up when the function is inputted with any other input. So the value of f of x itself is not important. What is important, that each input is mapped to a different output. So this is something to keep in mind. So let's now talk about a 2-to-1 function. So a 2-to-1 function is that if we have some input x, let's call it x1, and let's say it maps to some value v. So similarly, we can have another input x2, and that can also map to a value v. And then there might be another input that should map to some other value w, and there is going to be another input that matches to the same output. It doesn't matter what v is, what w is, as long as they're different. We can't have a situation that w is equal to v, because then it would be not 2-to-1, maybe 3-to-1 or some other function. So similarly, if there is some x7, x5, this is equal to some u, so there is some x6 that also gives the same output. So two values of the input are being mapped to single output. So this is a 2-to-1 function. And let me take an example here again. So let's say this is our input x, and this is some function f of x. Now there is one way of generating this 2-to-1 function is that we choose a secret bit string b, and let me call it actually p. Let me call this secret bit string p this time. And then if we have let's say, for the sake of argument, let me take this secret bit string as 0, 1, 0, and I have first input some 0, 0, and let's say I get some function f0. Now when I have I can come up with another input, and let's get that input by okay, for the moment let's say this is f0, and then there is some input 0, 0, 1, and suppose value of function is f1, and then let me XOR this p with x. So if this is x, if I XOR with this secret bit string, so this 0, 0, 0 is going to be XORed. So 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 0 is 0. So there's going to be another number 0, 1, 0. For this input, the function give the same output. Similarly, for this 0, 0, 1, if I XOR this 0, 0, 1 with x, so I get 0 plus 1, 1, 1 plus 0, 1, 0 plus 0. So for 0, 1, 1, I get the same output as f11. Similarly, for 1, 0, 0, and let's say the value of function is some f2, but if I XOR 1, 0, 0 with the 0, 1, 0, so this secret bit string p is fixed, 0, 0 plus 0, 1, 0, 1, 1 plus 0, 1. So for 1, 1, 0, I get the same output f2. For 1, 0, 1, let's say the value of the function is some f3. So if I XOR 1, 0, 1 with 0, 1, 0, 1 plus 0 is 1, 0 plus 1, 1 plus 0, 1. So for 1, 1, 1 input, I have the same value of the function as f3. So now you see this function maps this input and this input to the same output. So this input and this input to the same output and so on. And this time the secret bit string was this P010. So we generated a 2 to 1 function by doing this thing that we said, okay, let's start with the input bit string, so 0 0 0 0 1 0 1 0 etc. And then we XOR the input with some bit string P, and for the same bit string for which this this X and X plus B X plus P is the same, we get this function. And there's another thing with this you can notice easily. If I have this 0 1 0 number and this 0 0 0 for which the inputs are the same, if I XOR this 0 1 0 0 1 0 with 0 1 0, I get 0 0 0, because 0 plus 0 is 0, 1 plus 1 is 0, 0 plus 0 is 0. So it doesn't matter you XOR this P string with 0 or 0 1 0, they both map to each other. So similarly, we have the same output for 0 0 1 and 0 1 1, and you can see that if I add P into this, if I add P to 0 0 1, I get the second input. And if I add P to this second input 0 1 1, if I add this bit string P to this one, so 1 plus 0 is 1 0 0. So if I add P here, I get this one, and if I add P here, I get this one. So there is this symmetry. So you don't have to worry, okay, if I'm going in order, which bit string should first come in. So this is one way of building this 2 to 1 function systematically. So is everybody okay with this scheme? Okay, so you can say, okay, why do we have to add this bit string? All our Simon's problem concerns with this thing that we just have to implement a 2 to 1 function. It doesn't say anything with a string about XORing the input with a bit string. So let's come up with another function, and then we will see that this bit string automatically this idea is equivalent to that. For example, you have an input 0 0 0 0 1 0 0 1 1 1 0 0. So did I miss anything? Yes. So 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So actually, this time what I'm going to do, I'm going to ask some of you to tell me which of the two inputs should have the same output. Doesn't matter what output, but they should have the same output. So let's say if I ask Abdullah Ahmed, would you like to choose a combination of inputs that should have the same output?
Sir, for example, 0 0 0 0 1 1.
Okay, so you want this one and this one to have the same output. So let me just label this output some F1, and for this some F1. Okay, what two other?
1 1 0 0 1 0.
So 1 1 0 sorry 1 1 0 and
0 1 0.
So let's say this should have some F2, and this should have some F2, and
1 0 1 and 1 0 0.
1 0 1 and 1, so this and this one. Okay, so F3, good that you are not making any pattern. And okay, only two are left. So this one, let's say this is some F4 and this is some F4. So now let's see if can we find some bit string P that if I add 200, I get this thing. And similarly, you know, it works for the other input combinations as well. So in this case, you know, it's easy because if there's 000 and this is 011, so this can be, you know, one candidate is this 011. And for this one, if I add 2001, it becomes 011, 1 plus 1 is 0, 1, 0. So it was this, and this is not this. So it means that this is not going to work. And in this case, actually, this bit string I think is not going to work because there's no order. So if we have, you know, a 2 to 1 function, then we will have to, you know, have these things appear in order. For example, if this is F1, this is F1, and this is F4, F4 should come here. And if this is F2, F2 should come there, and so on. So if it, you know, comes with sort of periodic fashion, then we can make it with a bit string P. But if we can, you know, implement a black box that that, you know, doesn't give output in any order, then it cannot be, you know, thought of as XORing the input with some secret bit string P, so that this input Y is like the same. Or can we find some other secret bit string? So let's say if we have this 111, this is F4, where is F4? So there's F4 here. So if we look at this one and this one, this has to be 110, because if I put 110 with this, I get this, and if I put 110 here, I get this. So which is not, you know, 011. Okay, so so for this kind of functions where it is not periodic, we will have to come up with another scheme. But if we have a situation like this, let me rub it, that let's say if we have some F0 for this, and then this is also some F1, and then if we have this 001, it maps to some output F2, and then this maps to some output F2, and if this maps to some output F3, then this maps to some output F3. So in this case, if I think about this P, so 011, so if I add 011 to this, so I get I don't get this one. So this has to come up, you know. So if we have 000 and this is 011, and if you have 001, and if I add this 011 to this, 1 plus 1 0, 0 plus 1, 0 plus 0, so what is 011? So this one and this one should have the same output. So this is both F2, and 100 and 111, this should have same output. And if this is 101, this is 110, so 1 plus 0 is, so if I add this one to this, yes, so this is the pattern. So if we generate by XORing the inputs with the a secret bit string, then we get a definite pattern instead of, you know, the random bits. But okay, so any question about these 2 to 1 function? Because this way it's systematic to map, you know, this 2 to 1 function for each two inputs to go to a single output. And we will be able to construct an oracle easily also for this kind of relations between the inputs for which the output is to be found. Okay, so let me take another example. And let me actually show the plot quickly as well. So for example, if we see for this one, the plot is going to be something like this. Let's draw a plot. So this is input 0, 1, 2, 3, 4, 5, 6, 7. So we are saying the 0 and 0, 1, 1 has the same output. So let's say this output is sum this, and 0, 1, 1 is 2 plus 1, 3. So this one has the same output. And then 0, 0, 1, if I XOR it with 0, 1, 1, we get 1 plus 1, 0, 0 plus 1, 1, 0 plus 0, 0. So this 0, 0, 1 and 0, 1, 0. So 0, 0, 1 is this this one, and this is this. So these two have, you know, the same output, and then 1, 0, 0 and 1, 1, 1, they have the same output. So 1, 0, 0 is here, and this 7 is here. So they have the same output, and then 1, 0, 1 and 1, 1, 0 have the same output. So let's say this is something like this. So if I connect it, the shape of the function, you know, looks like this. And what I'm trying to say that these values themselves doesn't matter. For example, we could equivalently say that this is a function that gives the same value at this and this input, and let me call it this, and the same at this and this, and let's say they are this, and the same here and here, and suppose it is this, and the same here and here, and suppose it is this. So now if I draw the plot, looks like this. So this is a different function than the previous one, but still they both come from the same bit string P. So this value of the function itself is not important as long as it is a 2-to-1 function. So this 2-to-1 function and this 2-to-1 function, they're both being generated by the same bit string P because the inputs are related by this XOR relationship between the inputs. And that's why when we will be implementing an oracle that implements a function f of x that gives the same output if the inputs are related by this, you know, bit string P, then what we will have to, you know, keep in mind that there are multiple oracles that implement the same bit string P. And that essentially means that there are different values of the functions that this oracle maps to for the same input combinations. So if the bit string P is fixed, we still have multiple oracles. So it means that oracle in this case is not unique. This is something that we will have to keep in mind when we implement it in Qiskit. Okay, so any question? If not, let's now, you know, come to the algorithm itself. And let me first describe the algorithm. And then I will analyze it. So the algorithm is like this, that you prepare n bits in 0 state, and then you apply Hadamard on them. But then you also prepare another n bits in 0 state, and there is an oracle OF. No, this time this is not a phase oracle that applies to all of this in actually such a way that this input comes here. So if this is X is available here, and since this is 0, so f of X is coming here if this is X. And then we measure this part, and then let Hadamard be transformed, applied to the upper part, and then we do the measurement. And our claim is that the secret bit string would appear here at the output, that this state will actually not the secret bit string, but there will be some output, and we'll see that how we can use that output to find the secret bit string P. So this is a function, and there is this oracle in it. And let me talk a little bit more about this oracle. So this is a general oracle that we have discussed before as well. So this is an oracle that if you have an n bit input X, it gives that input at the output, and it takes another n bits as input, initialize to 0 state, and then it provides this function f of X at this output. Essentially, it XORs the f of X with the 0. So 0 plus f of X is f of X. So this is the oracle that we will be implementing. And there are a couple of differences, with respect to the phase oracle. Number one, that we don't have a single input, we have multiple inputs. And number two, we don't initialize this input, ancilia inputs, if you want to call them, to minus state, but we initialize them to the 0 state. And the number of bits over here and number of bits over here are the same. Okay, so let's analyze this algorithm, and for that let me call the state over here some psi naught, and state over here some psi 1, state over here some psi 2, state over here some psi 3, and then we perform the measurements. So let's begin with the psi naught. So our input state is 0. So essentially its total number of bits are 2n. So it's a 0 state, which I can also write like this. Let's keep writing it actually like this, because there are 2 quantum registers that we are now working with. So both registers have n qubits each. Okay, so this top register appears on the right, so this one, and the bottom register, this one, appears on the left. This is how we are keeping the notations. So let's see what is psi 1. So psi 1 is when you perform identity on the lower quantum register, and you perform an n-bit Hadamard transform on the upper quantum register. This is identity, so this becomes 0, and this we know what becomes. This becomes 1 over n square root. X goes from 0 to n minus 1 x. So this is what it becomes. And now we have to apply our phase oracle. And let me just show you what the action of phase oracle is. So phase oracle was like this. So if we have an n, so this remains in x, and this becomes f of x. So symbolically, if we operate our, sorry, not phase oracle, just oracle on 0x state, this gives us f of x, because it doesn't say it doesn't do anything to this one, and it changes this 0 to f of x. So let's now apply this phase oracle to this thing, and we get this state psi2 as applying this oracle sum over x. I can also write it like this, 1 over n square root and oracle to 0 sum over x. And now when this oracle is applied here, this becomes f of x. So this is the state right after this oracle. So this is the point. Now, after this stage, let's say we apply measurement on this f of x register. So since this f of x could have several values, this could be, this f of x could, when we measure it, it could either be f1, or it could be f2, or it could be f3, or it could be, the other f4. So f1, f2, f3. So let's call it some f4. So it could be one of these values. But once, let's say we do a measurement, and suppose, let me take a cleaner table to work with. Okay, so let's say we measure and we get f0. So if we get f0, our other register could be in either this 00 state, or could be in 01 state, 010 state, or more precisely, it could be in a superposition state of 00 and 010. Because when we measure in f0, and since our output state is already a superposition of all of these states, after this we will be, instead of sum, we will have only these two states in the x register. So let me explain it a little bit in detail over here. So let's say I expand it like this, 1 over n square root. So this is f0, 0 state, f1, 1 state, and so on. So let's say we continue, and there is some mth state. So value of function at that state is f of m. It's mth state. And then we continue, and then there's going to be a state where we have the same value of function f of m, and this state could be some m XOR p and so on. Okay, because for this state, which is being generated from this state by adding by XORing some bit string p, the value of the function here and here is the same. So it means that I can write it 1 over square root. So all of this, and from these two states, I can take f of m common, and then I have m state and n state, and where this n is equal to m plus p. Now, suppose when we do measurement, so this f register collapsed to this state f of m. Then my output right after this, measurement. So right after measurement, so this register would be in this state, while the other register would be in a state which is proportional to this. And if I write it in the normalized form, this would be m plus n. So you can't get, this 1 over square root 2 factor if you just keep looking here and say, okay, 1 over n square root is here and so on. The reason is this, that the measurement process is not a unitary process. Okay, so it's a collapsing process. So after this, each state has to be normalized manually by us again, in mathematics. So this is some state which is, normalized in itself, and this is a state which is in other register, and since it's m plus n for sure, so I have normalized it by adding a factor 1 over square root 2. So this is what we get to. So right after the measurement. And actually, let's not label this psi3, but let me label this as psi3. And now let's see what is psi4. So psi4, and actually since this register is measured anyway, so let's just forget this one and keep our eyes on this one. So this is nothing but the Hadamard, n-bit Hadamard applied to these states, and I can now write 1 over 2 square root Hadamard applied. So this is a bad name actually for n state, because I'm using this n symbol here. So let me use this is m n o p. Let's use it some q. So on m and Hadamard on q state, where q is m plus p. So let's use the definition of Hadamard. So sum over, I don't know, x minus 1 power m dot x, sum over x plus, and there's 1 over n square root, and let me take it common outside. So sum over y minus 1 power n dot y, y. And actually, since these are, the sum of states like minus 1 m dot 0 0 plus minus 1 m dot 1 1 and so on, and this is the same as well, minus 1 power n dot 0 0 state plus minus 1 power n dot 1 1 state and so on. So I don't actually have to use a different symbol for this. I can just use the same symbol, let's say x here, and I can combine them together. Sum over x minus 1 power m dot x plus minus 1 power n dot x into x. Okay.
Excuse me, sir. सर ये जो हमारे स्टेट्स हैं, जरा स्क्रॉल अप कर ले तो m और q स्टेट्स जो हैं, तो ये टेंसर प्रोडक्ट स्टेट्स तो नहीं है ना, वो तो हमने इधर से सम से निकाल लिए, ये सिंगल स्टेट्स नहीं है, और इसमें हम n हेडमार्क अप्लाई कर रहे हैं।
हाँ, ये भी n बिट स्टेट है, ये भी n बिट स्टेट है,
ये n बिट स्टेट्स हैं।
जी जी,
ठीक है सर, थैंक यू।
मैं जैसे देखे ना, ये m और q, इफ यू गो टू द टेबल, तो ये वो स्टेट्स हैं जिनके लिए फंक्शन की वैल्यू स्टेट है. सो लेट्स से इफ m इज 0, then q is 0 1 0. If m is 0 0 1, then q is 0 1 1, because this m and q are related by this XOR operation, because for both of them the value of the function is the same.
इस स्पेशल केस के लिए m is equal to 3, ये जो टेबल है,
ये n is equal to 3 है, ये 3 बिट एग्जांपल है.
ठीक है सर, सही है, थैंक यू.
Thank you. Okay, so अब ये देखें, ये हम दो नंबर्स को ऐड कर रहे हैं. So this number can be either -1 or +1, because this power can be either 0 or 1, right? So this is a dot product. If you remember, bitwise, you first multiply corresponding bit and then sum XOR 2. So this number modulo 2. So this number is either minus or plus. So for any state X for which this is equal to this, you will have some non-zero amplitude. And for any state X for which this is not equal to this, which means that if this is minus, this is plus, and if this is -1, this is +1. Then if you add minus and +1, you will get a 0. So when you do a measurement now, you will get you will measure only those X for which this -1 m dot x is equal to -1 n dot x, that either they are both minus and minus, so that you sum and becomes -2, or they both +1 and +1, so that when you add they become +2. Only for those state X you will see some amplitude at the output, because if they are both different, if one is -1, other is +1, the sum is 0, and that state will not appear in the measurement statistics. You see, if this is a 3-bit example, this psi4 is nothing but a state like 000 with some amplitude plus 001 with some amplitude, and so on. And when I measure psi4 many times, I will get a histogram, and only those state with, I don't know, some probability present here for which this amplitude is non-zero, because wherever this amplitude is 0, that state will not appear in the histogram. And now we can see that for this amplitude to be non-zero, both of these terms have to be equal, because if they are equal, it doesn't matter they are both -1 or both +1. If they're equal, the sum would be non-zero, and we will be able to measure that state in the output statistics. Okay. All right. So this means that if this is equal to this, this can only happen if m dot x is equal to n dot x. Sorry, I'm again using this n, but I should have been using q here. Q because I changed the state to q. Q. So where this q is m XOR p. So if I distribute this product over m and p, because this is nothing but plus, so I get m dot x plus p dot x. But this m dot x can be cancelled from both sides, so 0 is equal to p dot x. So it means I will observe only those states at the output which has the dot product with p equal to 0. So just to give you an example, if your secret bit string is 011, so can you figure out what are the possible X states for which you will see this histogram? So let's check each one. So if X is 000, X dot P is 0. So 000 state will appear in the output. In fact, it doesn't matter what P is. Okay, whatever P is, this 00 state will always be present in the output, because its dot product with P is always 0. So let's check 010. So if 001, so 001 into 010 will give me 1 into 1, 1, 1 into 0 plus 0, 0 into 0, 1, not equal to 0. So this 001 state will not appear in the output if the secret bit string is P. So at the end, what will happen, that we will have bunch of outputs. So let's say I have some p dot x1, and there might be some, another output which is non-zero, and there might be some other output which is non-zero. And from these equations, let me write it, p2 x2, p1 x1, p naught x naught 0, p2 x2, p1 x1, p naught x naught, p2 x2, p1 x1, p naught x naught. But this x2, x1, x0 are bits of this, x1 output. So let me call it this, and this x2 is from the second output, and these are the bits of this third output. So we will have to solve this matrix because these x's are going to be known by looking at the histogram, and we have to find this p2, p1, p0. So basically, we have to solve this matrix using some techniques to really find this bit string p. And there are efficient classical methods available to solve this, matrix equation, and they usually require operations of the order of n power cube. So basically, you need n power cube number of operations plus 1 on quantum computer to find this bit string p. And if this p is 0, we will mean that the function is 1-to-1, because for any input x, if you add p to it, it will remain that. So there's no other unique input which is going to be so. So if this p is 0, this y is equal to x. So essentially, for 2-to-1 function, this p has to be non-zero so that y and x are different, for which the function has the same output. So if p is not 0, then this is a 2-to-1 function. So on a quantum computer, with one operation on quantum computer and an n cube classical operation, we can find this value of bit string p that will tell us if the function is 2-to-1 or 1-to-1. On the other hand, to work out whether this function f of x is a 2-to-1 or 1-to-1 function, we will really have to give all the input over here and then record outputs. And actually, if this is n bits, there are capital N possible inputs, which are like 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and so on. So there are n possible inputs here, and you will have to give at least half of them. Okay, so at least n by 2 before you are able to see for sure, for the worst case, that this is a 2-to-1 or 1-to-1 function. Because if after half input, when you give the next input, if this function repeats if there's output which is the same as given by in one of the previous input, you'll be able to say, aha, it's a 2-to-1. And if after half it still gives you a different output, then you can say, okay, this is a 1-to-1 function, because for more than half inputs it has given the same different inputs for each input. So this number n is 2 power n. So 2 power n by 2 is 2 power n minus. So this is exponential. And it doesn't matter if you have access to a random number generator, because even if you give inputs here randomly, like all different inputs randomly, but in the worst case, it is still possible that the random selection that you make, they all have a unique output. And then after n by 2 plus 1 iteration, when you give the next input, you might get either the same or different output. So even with a probabilistic, classical computer, you still have the worst case scenario that you require 2 power n minus 1 inputs to this black box before you are able to see if this implements a 2-to-1 or 1-to-1 function. So classically, you require exponential number of steps. And if you have access to quantum computer, and a classical computer. So using both, you can now find this bit string p in n cube number of operation, which is only polynomial. And if this p is 0, you can say this is a 1-to-1 function. If p is not 0, you can say this is a 2-to-1 function. So any question? Okay, so let's take a 10-minute break, and then I'll explain how to implement, how to design an Oracle for this Simon problem, and then we will see its implementation in Qiskit.